Hello everyone, my name is Baiwen. Today I'm gonna talk about our recent work on the dynamic modeling and hierarchical control of a microgrid incorporating ammonia. This work is done by me and my advisors Qizhang and Prodromos Stavtidis. So the basic motivation of this work is to use ammonia for energy storage. Ammonia is known as an important chemical in multiple industries and in agriculture, but can also be used to store renewable energy through the power-to-ammonia process. In this process, the renewable energy can be used to power water electrolysis, for green hydrogen production, and power air separation for green ammonia production. And this hydrogen and nitrogen can be used to produce ammonia through the Haber Bosch process. And the power generation from green ammonia can be through gensets or the fuel cells. There are multiple advantages of using ammonia for energy storage. The first is that ammonia itself is carbon-free, so the production and combustion of ammonia will not emit any CO2 to the environment. And ammonia can be easily stored as a liquid. It can be stored at the ambient temperature and immediate pressure, and it has a very high energy density but a pretty low storage cost. So the energy density of ammonia is much higher than that of batteries or the gaseous hydrogen, but the storage cost is less than 1% of storing hydrogen. And in this plot, it compares several energy storage technologies in terms of energy capacities and the storage duration. And we find ammonia is one of the most well-suited solution for storing a large amount of energy and for long-term energy storage. So given those merits of ammonia, it's natural to consider incorporating into a microgrid as an energy storage unit. A microgrid is an integration platform for power supply, storage units, and energy resources. And here the energy storage units play an important role in the microgrid to resolve the mismatches between the renewable energy and the power demand. And here, it shows a diagram of an islanded microgrid incorporating green ammonia. The wind energy and solar energy are captured as energy input to the system, and there are the production units, storage units, and the conversion to power units of hydrogen and ammonia. And the local power demand can be met either from the renewable energy source or from the power generation from the energy storage units. The optimal design of such a microgrid incorporating green ammonia has been studied. However, such studies only focus on the design and the scheduling problems, with neglecting many details in the process, such as the hydrogen production or ammonia production. And the feasibility of the real-time operation and control of such a system has not been demonstrated yet. So let's talk about the operation and control of microgrids. There are actually various control strategies proposed and implemented for microgrids, such as the centralized control, distributed control, and hierarchical control. But the real-time operation and control of a microgrid incorporating ammonia synthesis, storage, and conversion to power has not been explored yet. There is a new challenge that ammonia synthesis, the ammonia can bring to the control of microgrid. It's because ammonia synthesis process is pretty slow. The ammonia production is subject to the available renewable energy and the hydrogen inventory, so it cannot be produced at a constant rate all the time. But the transition between different production rates are very slow, can take up to hours to finish. And this may cause the depletion of energy storage media or even the failure to meet power demands if there is not a proper strategy to regulate storage inventories and meet the demands. So proper control architecture is needed. So here it comes to the problem that we are trying to solve. We're considering a real-time operation and control of an islanded microgrid with both hydrogen and ammonia for energy storage. And in this system, the wind and solar energy are the only energy sources, and the demand to be met here is the residential demand. The power exchange with the main power grid is not in the discussion. And we want to have a control strategy that can meet the local power demand and maintains the stability of the system, such as the temperatures in the reactor beds and at the membranes and the pressures in the storage tanks, and want to minimize the operating cost of the system. So the challenges include the intermittent nature of the wind speed or solar irradiance, and the ammonia synthesis process is slow, like we already mentioned. And also, even though we can get some forecasting data of the wind speed or solar irradiance, but the actual data can be very noisy. So to address those challenges, what we adopt is a two-layer hierarchical control structure. It consists of two layers. The D-RTO layer works as a supervisory layer, which minimizes the levelized operating cost by solving an optimization problem with a receding time horizon. It can get the forecasting demand profile and the prediction of the renewable energy source data and the real-time storage inventories through a communication with the local layer, and make decisions on a bunch of variables such as the power used for electrolysis, the storage inventories, and the ammonia production rate. The local layer actually refers to the local controllers in the subsystems. And most of these local controllers are linear controllers to enforce the commands from the D-RTO layer. And these decisions or the commands are updated hourly. So it means the RTO's problem is solved at each hour. So let's first take a look at the real-time optimization layer. The override function is to minimize the levelized operating cost, which consists of three parts: the cost of hydrogen ammonia storage, the cost of hydrogen ammonia production, and the cost of converting hydrogen ammonia to power. The decision variables include the power generated from hydrogen ammonia, the power used for electrolysis, the production rate of hydrogen and ammonia, and the storage inventories. Parameters include the residential demand and available wind solar power from the forecasts, and the real-time inventories, which came from the communication with the local modules. And the constraints include the power balance, the hydrogen production, the relation between the hydrogen production rate and the power for electrolysis, the ammonia production rate and the hydrogen consumption, and the power generation from the chemicals, the inventory balances, and the lower and upper bounds. Now let's take a look at the local control layer. Here are a few examples of the local subsystems. In the ammonia synthesis module, there is a heat exchanger that can preheat the synthesis gas to a desired temperature. And there are 3 plug flow reactor beds to synthesize ammonia. And there's a flash tank that can separate ammonia as a liquid, and the vapor is recycled back to the reaction system. And here we have 3 PI controllers to control the feed temperatures to each reactor bed by manipulating the feed flow rates. In the water electrolysis module, we have a membrane system, the anode fluid channels, the cathode channels, a dehumidifier that can remove water from the hydrogen, and a small buffer at the output of hydrogen flow. And here there are 2 PI controllers to control the temperature as membranes and the pressure at the hydrogen buffer. And in the wind power module, we can manipulate the pitch angle and the generator speed to regulate the power output based on the wind speed. And these controllers are also PI or PID controllers. So let's talk about the case study. Here we pick 3 locations for the study, which are Duluth in Minnesota, Phoenix in Arizona, and Las Vegas in Nevada. And these locations have different installed capacities, which are based on the design paper. In Duluth, it has a rather large wind turbines installed, but a very small PV array, and has a medium size of the ammonia storage unit. In Phoenix, it has no wind turbines, but a super large PV array, and has the largest ammonia storage unit. While in Las Vegas, it has the smallest RES, smallest storage units, and the smallest ammonia or hydrogen production units. And for each of these locations, two representative days in different seasons are picked for the simulation. And here we consider the noisy wind speed and solar radiance profile. And here is an example. The blue line is the noisy wind speed, and the red one is the solar radiance. We can find there is a peak in the middle of the day of the solar radiance. The process model is constructed in MATLAB Simulink, and the real-time optimization problem is formulated in PyOmo and solved by the solver Groby. So let's first take a look at the results of Duluth. So here it shows a power balance plot. The positive values are about the power consumption, which include the power used to meet the local demand and the power used for water electrolysis, while the negative values are the power generation, which can be either from the RES or from the storage units. And we can note that there are some fluctuations in the wind power and in the electrolysis. These fluctuations are due to the noisy RES, as the plot we just saw in the previous slide. So in Duluth, there is little solar energy, but the wind energy is pretty abundant, and especially in winter. So you can almost power the water electrolysis all the time, and the electrolysis actually contributes to most power consumption. While in summer, the solar energy and wind energy are not sufficient to meet the demand, so the dispatch of hydrogen or ammonia is needed. So this plot shows the ammonia production rate. So we can find the transition is pretty slow, especially at the start. So what's happening here is that there is a temperature rising, and it takes a lot of time and can be around 1 hour. And we can see some disturbance in the feed temperature to the first reactor bed. But the steady production is after the transition, say in 1 to 2 hour transition of the ammonia production unit, and it can still still tracking the set point of the production rate. And here, this plot shows the ammonia storage profile in summer and winter. We find even though there are occasional deviations from the real-time storage inventory and the set points, the D-RTO commands are in general very well enforced. And the ammonia storage inventory is accumulated in winter, and the frequent combustion of ammonia is found in summer, which is consistent with what we saw in the power balance plot. Now let's talk about the case in Phoenix. The story here is very different, because the solar power is the only renewable energy source, and it's only available in the daytime. So, and there is a huge difference in the residential demand in spring and summer. In spring, the residential demand is pretty low, so that the solar energy is more than enough to meet the demand during daytime. It can power the hydrogen production. But late in the day, when there is no solar energy, the dispatch of hydrogen is needed to meet the daily mismatch between the power supply and the power demand. And in summer, the residential demand is pretty high, so that we find the dispatch of ammonia is further needed. And we can find the ammonia inventory slowly increases in spring, but decreases in summer to meet the power demand. In Las Vegas, it has rather evenly distributed RES through the year, so we can find similar patterns of energy usage in spring and fall. And most the power demand can be met directly from the renewable energy source. So that also explains why it needs the smallest storage capacity among these three locations, because most of this demand can be directly met from the solar or wind. And finally, we made a comparison of these three locations in terms of the daily cost. So we find that, so the left bar represents the daily cost of the microgrid ammonia, and the right bar represents the cost of the microgrid with only hydrogen. And we find the hydrogen storage is a dominant daily cost in a hydrogen-only microgrid, shown as the pink bar. While for ammonia, for a microgrid with ammonia, the dominant parts are the ammonia-related production, storage, and the orange one, which is the ammonia storage. And by introducing ammonia, the daily cost can be reduced by at least 23%. And there is a case, which is the Duluth in winter. We find there can be even cost reduction as high as 60% by incorporating ammonia. The more the microgrid relies on energy storage, the more it can benefit from incorporating the green ammonia for energy storage. And in summary, in this work, we have a dynamic modeling of the microgrid incorporating green ammonia production, storage, and conversion to power. And we demonstrated the feasibility of the real-time operation of the system by implementing a two-layer hierarchical control. We find that residential demand power is met, which is a priority, and the RTO commands are in general very well enforced. And we have reviewed the geographic differences of these locations in the operation aspect. And finally, we note there are significant economic benefits of incorporating ammonia to the microgrid. So thank you for attention. I'm happy to answer any questions you have.